All right, so in this video, we're going to solve the following system of differential equations. So how do you suppose we solve a system like this? Well, we could solve this system by using the eigenvalue method. And so to do that, we'll first convert this system into a matrix equation. So basically, this matrix equation is in the form of x prime equals px. The next thing we need to do is we need to determine the eigenvalues of matrix P. So to determine the eigenvalues of this matrix, we basically take the determinant of this matrix, but we modify it slightly. We're going to take these two entries and subtract lambda, and then we're going to set this determinant equal to 0 and solve for lambda. Lambda is what we call an eigenvalue of this matrix. So if you recall, the determinant of a 2 by 2 matrix is this times this minus this times this. And so if we were to algebraically simplify this, we would get. And so at this point, we have a quadratic equation, which can easily be solved by factoring. And so these are the two eigenvalues for our matrix. We get -4 and 2. So now what we need to do with these eigenvalues is we need to determine an eigenvector that corresponds to each of these eigenvalues. We'll start with our first eigenvalue. So how do we determine an eigenvector for an eigenvalue? Well, we can do that by using the following matrix equation. This matrix equation, right? Lambda1 is our eigenvalue. V1 is an eigenvector corresponding to that eigenvalue. So remember, matrix P is the same matrix that we've been dealing with right here. So lambda1 in this case is -4. I is the identity matrix. Now in this case, since P is a 2 by 2 matrix, we have to use the 2 by 2 identity matrix. V1 is our eigenvector, which in this case, since we have 2 by 2 matrices, that means that our eigenvector is going to have 2 entries, which I'm just going to call V1 and V2, right? And we're setting this matrix equation equal to the 0 vector. Well, since we have 2 entries here, we're going to need 2 entries that are both 0 for our 0 vector. And so what we need to do now is we need to determine a non-zero number for V1 and for V2 that satisfies this matrix equation. And that would be an eigenvector that corresponds to this eigenvalue. So to do that, let's first simplify this thing. If you were to simplify this, you would get this. And so now we can multiply these two matrices together using matrix multiplication, and we would get this. Basically, we now have 2 matrices of the same size equal to each other. We can say that this is equal to 0 and this is equal to 0. But here's the thing. These two equations are the same, so we only have to consider one of them when determining the eigenvector. Turns out, there are infinitely many choices for V1 and V2 that satisfies us. We just need to choose one particular choice, right? But V1 and V2 cannot equal 0, right? They have to be non-zero. And so I like to choose V1 and V2 such that they're both integers. That's the way I like to do it. So what we can do is we can say that V1 is equal to 1. Well, if we decide to choose V1 to equal 1, then that would mean that V2 has to equal 7. Because 7 times 1 minus 7 equals 0. So really, this pair for V1 and V2 satisfies this equation. And therefore, our eigenvector could be 1, 7. So this is an eigenvector corresponding to this eigenvalue. So I'm actually just going to write these two things off to the side for safekeeping. And so now that we've determined an eigenvector for lambda1, now we need to determine an eigenvector for lambda2. So we're basically going to do the same thing that we just did, right? We're going to use the same matrix equation that we used before, where V2 is an eigenvector corresponding to lambda 2. So now, matrix P is the same thing as before. Lambda 2 is 2 in this case. I is the same identity matrix as before. V2, in this case, I'm just going to represent my eigenvector with the same sort of notation, right? And this is equal to the 0 vector, same exact way as before. Again, we need to determine a non-zero number for V1 and for V2 that satisfies this matrix equation. Just like last time, I'm just going to simplify this thing right here. And so at this point, we can now multiply these two matrices together, and we would get. And so this is what we get now. So really, now we have two matrices of the same size equal to each other. We can set this equal to 0 and this equal to 0. But here's the thing. If you were to take this second equation and divide 7 on both sides, it would be identical to the first equation. So really, these two equations are identical to each other, so we only need to consider one of them. It turns out that'll be the case no matter what you have here. It'll always be the same whenever you're computing an eigenvector. You only need to consider one of these things, no matter what. In this case, I'm going to consider the first one because, well, that's easier to work with. So for instance, if I choose V1 to equal 1, then that would imply that V2 also has to equal 1. And therefore, the eigenvector would be 1, 1. So this is an eigenvector corresponding to lambda 2. So now that we have the eigenvalues and an eigenvector corresponding to each of those eigenvalues, this is enough to write the general solution to this system. Turns out we can represent the general solution to this system as. And so now if we just perform the substitutions for each of these four things into this thing, we would get. So this would be our solution to this system, right? And so this is basically it for this video.